NEC 110.3 addresses nameplates on electrical equipment. Specifically, it states that the nameplate of listed equipment, excluding utilization equipment, must be legible and include certain information. Among this information is the rating of any overcurrent protective device of the branch circuit supplying the equipment when that protected device isn't an integral part of the equipment itself. This means the equipment's nameplate should clearly show the required overcurrent protection rating for its branch circuit. In the scenario presented, the subpanel is considered the equipment according to the NEC. The new 3-pole, 70-amp breaker serves as the branch circuit protective device. Therefore, NEC 110.3 would require the subpanel's nameplate to be marked with 70 to indicate the appropriate breaker rating. If the nameplate doesn't reflect this 70-amp rating, it constitutes a violation of the NEC. However, it's crucial to understand that this requirement applies only to listed equipment. If the subpanel in question is not listed, meaning it hasn't been tested and approved by a nationally recognized testing laboratory, or NRTL, then NEC 110.3 doesn't apply. In such a case, there would be no nameplate violation based solely on this section of the code. Now, let's consider the feeder conductors and overcurrent device. The question mentioned using number 4 conductors for the new feeder, with an actual current draw of 35 amps and a 3-pole, 70-amp breaker. The conductors must be appropriately sized for both the load and the overcurrent protection. Number 4 copper conductors, according to NEC Table 310.16, have an ampacity of 70 amps when using a temperature rating of 60 degrees Celsius or 75 degrees Celsius. Therefore, the number 4 conductors are sufficient to handle the 35-amp load and are also protected by the 70-amp breaker. As long as the conductors are installed in accordance with all other applicable NEC requirements, such as proper termination and protection from physical damage, the feeder installation itself appears to be compliant. To summarize, firstly, the NEC 110.3 violation hinges on whether the subpanel is a listed piece of equipment. Secondly, if it is listed, the nameplate must reflect the 70-amp breaker rating. Thirdly, if it's not listed, this particular nameplate requirement doesn't apply. Fourthly, the feeder conductors and overcurrent device appear to be appropriately sized for the load, assuming all other NEC requirements are met. It's crucial to consult the specific product listing and labeling information for the subpanel to determine if it is indeed listed and what specific markings are required. Additionally, always refer to the latest edition of the NEC and consult with a qualified electrical inspector to ensure full compliance with all applicable codes and regulations. It is important to consider the full scope of the installation, including conductive type, termination methods, and environmental factors such as ambient temperature when verifying compliance. For example, the ampacity of the conductors may need to be adjusted based on the number of current carrying conductors in a raceway or cable, or based on the ambient temperature where the conductors are installed. It's also crucial to verify that the equipment is properly grounded and bonded to ensure electrical safety. Bonding is the permanent joining of metallic parts to form an electrically conductive path that ensures electrical continuity and the capacity to conduct safely any fault current likely to be imposed. Grounding is connecting the electrical system to the earth to provide a low impedance path for fault current, helping to protect people and equipment from electrical shock. NEC Article 250 provides detailed requirements for grounding and bonding. Regarding the overcurrent protection, it is important to verify that the breaker is properly rated for the specific application. This includes considering the interrupting rating of the breaker, which is the maximum fault current that the breaker can safely interrupt. The interrupting rating must be equal to or greater than the available fault current at the point of installation. The available fault current can be determined by performing a fault current study, which typically involves calculations based on the utility transformer impedance and the impedance of the conductors and equipment in the electrical system. Furthermore, the breaker must be of the correct type for the equipment it is protecting. For example, some equipment may require a specific type of breaker, such as a high magnetic breaker, to provide adequate protection. It is also important to consider the coordination of overcurrent devices in the electrical system. Coordination refers to the selective tripping of overcurrent devices such that only the device closest to the fault opens, minimizing the disruption to the rest of the electrical system. This can be achieved by using breakers with different time current characteristics. When dealing with electrical installations, it is always recommended to consult with a qualified electrical engineer or inspector to ensure that the installation is safe and compliant with all applicable codes and regulations. They can provide guidance on selecting the appropriate equipment, sizing conductors and overcurrent devices, and performing necessary calculations to verify compliance. They can also identify potential hazards and recommend corrective actions. Remember that electrical work can be dangerous, and it is important to take all necessary precautions to protect yourself and others from electrical shock and fire hazards. Always de-energize circuits before working on them, use appropriate personal protective equipment, and follow safe work practices. The NEC is a comprehensive set of rules and regulations designed to ensure the safe installation and operation of electrical systems. Staying up to date on the latest edition of the NEC and understanding its requirements is essential for anyone involved in electrical work. In addition to NEC 110.3 and 250, other relevant NEC articles to consider for this installation include Article 215, which covers feeders, Article 220, which covers branch circuit, feeder, and service calculations, and Article 310, which covers conductors for general wiring. These articles provide detailed requirements for sizing conductors, calculating loads, and selecting appropriate overcurrent protection. Article 215 addresses feeder requirements, including ampacity, overcurrent protection, and grounding. It outlines the rules for determining the minimum size of feeder conductors based on the calculated load in the applicable ampacity tables. It also specifies the requirements for feeder overcurrent protection, ensuring that the feeders are adequately protected against overloads and short circuits. Article 220 provides the guidelines for calculating branch circuit, feeder, and service loads. It covers various methods for calculating loads, including the standard method and the optional method. It also provides specific requirements for calculating the loads of different types of equipment, such as lighting, receptacles, and appliances. Accurate load calculations are essential for properly sizing conductors and overcurrent devices. Article 310 covers conductors for general wiring, including their ampacity, insulation types, and installation requirements. It provides detailed tables listing the ampacity of different types of conductors based on their size, insulation temperature rating, and installation conditions. It also specifies the requirements for conductor identification, such as color coding, and the rules for directing conductors based on the number of current-carrying conductors in a raceway or cable. All these articles, when combined with the initial section we discussed, provide a robust framework for ensuring safe and compliant electrical installations. Remember, electrical codes and regulations are constantly evolving, so it's essential to stay informed and consult with qualified professionals to ensure compliance. Ignoring these details can lead to unsafe conditions, code violations, and potential liability issues. Always prioritize safety and accuracy in your electrical work. The NEC also has chapters that cover special occupancies, special equipment, and special conditions. For example, there are specific requirements for electrical installations in hazardous locations, such as areas where flammable materials are present. There are also specific requirements for electrical installations in healthcare facilities, such as hospitals and nursing homes. These special requirements are designed to address the unique hazards and challenges associated with these types of occupancies and equipment. It is essential to be aware of these special requirements when working on electrical installations in these types of locations. The NEC is not a design manual, but it provides the minimum requirements for safe electrical installations. It is the responsibility of the electrical designer or installer to ensure that the installation meets these minimum requirements and is also suitable for the specific application. This may involve going beyond the minimum requirements in some cases to ensure safe and reliable installation. For example, The NEC may allow a certain size conductor to be used for a particular load, but the designer may choose to use a larger conductor to reduce voltage drop or to provide additional capacity for future loads. It is always better to err on the side of safety and to use good engineering practices when designing and installing electrical systems. The electrical industry is constantly evolving, with new technologies and products being introduced all the time. It is important to stay up to date on these developments and to understand how they may affect electrical installations. For example, the increasing use of LED lighting has led to changes in the NEC requirements for branch circuit and feeder calculations. It is also important to be aware of the latest safety standards and best practices for electrical work. Organizations such as the National Fire Protection Association, or NFPA, and the Institute of Electrical and Electronics Engineers, or IEE, publish standards and guidelines that can help to ensure safe and reliable electrical installations. Continuing education is essential for anyone involved in electrical work. There are many opportunities to attend training courses, seminars, and conferences to learn about the latest code changes, new technologies, and best practices. Staying informed and knowledgeable is crucial for providing safe and professional electrical services. Finally, it is important to remember that electrical work is not a do-it-yourself project. It requires specialized knowledge, skills, and tools. If you are not a qualified electrician, you should not attempt to perform electrical work. Always hire a licensed and insured electrician to perform electrical work in your home or business. This will help to ensure that the work is done safely and correctly, and that it complies with all applicable codes and regulations. The subpanel in the initial question, if it is a listed piece of equipment, will have a listing mark on it from a nationally recognized testing laboratory, or NRTL. Examples of NRTLs include Underwriters Laboratories, or UL Intertek, and CSA Group. The listing mark indicates that the subpanel has been tested and certified to meet certain safety standards. The listing mark will typically be located on the nameplate of the subpanel, along with other information such as the voltage and current ratings. If the subpanel does not have a listing mark, it is considered to be unlisted, and the requirements of NEC 110.3 would not apply. It is important to note that even if the subpanel is unlisted, it must still comply with all other applicable requirements of the NEC. For example, the conductors and overcurrent devices must still be sized correctly, and the equipment must be properly grounded and bonded.